Welcome everyone. In this video, we will solve a problem on Mosfet circuit at DC, and it is from the Microelectronics circuits book. Okay, so the question is, consider a process technology for which minimum channel length, that is our L minimum, is given 0.4 micrometer, oxide thickness TOX 8 nanometer, mu n mobility of the NMO, and 450 centimeter square volt per second, and threshold voltage VT 0.7 volt. So we have to find COX, oxide capacitance, and K and S. Okay, process transconductance parameter. Option means the A number question is that. B number for a MOSFET with W by L aspect ratio 8 micron by 0.8 micron. Calculate the value of VGS, get to source voltage, and minimum value of VD needed to operate the transistor in the saturation region for a DC current 100 microampere. ID value is 100 microampere given, so we have to find the VGS and minimum VD. Now the third one is the for the device in B. Okay, so for the B condition, find the value of VGS required to cause the device to operate as a 100,000 ohm resistance or 1 kilo ohm resistance for a very small VDS. So this one is the question. Everything is given. Okay, so we have to first do it for the part A. For the part A, we have to find the oxide capacitance COX. So this COX can be written as epsilon naught X by TOX. So this one is the formula. So now epsilon naught X can be written as 3.45 into 10 to power minus 11 farad per meter. Okay, divided by oxide thickness TOX is given here 8 nanometer. So 8 nanometer. So I am just writing 10 to power 9 meter. Okay, one more thing for the epsilon naught x, that is our 3.9 epsilon naught. This one is simply our permittivity of the silicon oxide of the SiO2. So if we solve this one 3.9 and this one is epsilon naught, okay, it's simply our 8.854 into 10 to power minus 12. Okay, and if we solve, it will come 3.45 into 10 to power minus 11 farad per meter. Okay, so this one is also important. The epsilon naught x value will be 3.45 into 10 to power minus 11. So that we have written here. So now 10 to the power minus 9. So if we solve this one, 3.45 divided by 8 into 10 to the power minus 2. Okay, and if we solve 3.45 divided by 8, it will come nearly 0.43125 into 10 to the power minus 2, or in general sorry this COX can be simply, we can write 4.3 2 into 10 to the power minus 3. Unit will be farad per meter square. So it should be farad per meter square. So this one is the first part. Okay, farad per meter square for this COX value. Now we have to go for the process conductance parameter. So we have to very careful about the unit, all these things. So now next for the B, means K and dash. Okay, K and dash, simply we can write K and dash equals to mobility of this one mu and COX. Okay, so mu n value is given 450. So I am writing with full unit volt second, and COX. Okay, COX is equal to 4.32 into 10 to the power minus 3 farad per meter square. So now we have centimeter square and here meter square. So we have to make it same unit. So what we can write, 1 centimeter equals to 10 to the power minus 2 meter. So 1 centimeter square means 10 to the power minus 4 meter square. So what we can write, this can be written as 450 into 10 to the power minus 4. One can write meter square volt second 4.32 into 10 to the power minus 3 farad per meter square. So if this one, this should be cancelled out. Okay, now one can write 450 450 into 4.32 into 10 to the power minus 7. Now this one is farad by volt second. Okay, this one is capacitor unit. Okay, why I am writing, see, capacitor unit is this one, farad capacitor, this one is farad. Okay, so basically if we, now this, why I am writing, so q equals to cv, q equals to it cv. So c value can be written as it by v, means ampere second by volt. So capacitor unit can be written as, that is our farad. Okay, that is our farad, can be written as ampere second volt. Okay, so here this one is volt second is there, and farad is ampere second, oh sorry, ampere second by volt. So this second cancel, so ampere by volt square. So if we solve this one, 450 into this one 4.32, okay, and this one is minus 7. So if we write in microampere, 10 to the minus 6, okay, or one more line better, 450 to 4.32 into 10 to the minus 6 by 10. Okay, I am putting one zero down. So 45 into 4.3, and this should be ampere per volt square, and this one will be microampere, this one will be micro. So 45 into 4.32, it will nearly come 194 microampere per volt square. This one I am writing as a micro, so microampere per volt square, and overall value 194 microampere per volt square. Okay, so this one is just simply our k and s. Okay, I am writing here k and s is 194 microampere, approximately it should be around 194.4, so I am just writing this 194 microampere per volt square. Okay, this one, so this one is the second part. Okay, for the option, for the question A. Now we have to move for the part B of this question. Okay, so here I am writing, I am taking blue color pencil. Okay, okay, for B. So B, the transistor, we have to operate the transistor in the saturation region. So first, Mosfet is in saturation region. For the part B, it's in the saturation region. So I am writing this. Okay, Mosfet is a saturation region. Okay, having that ID value 100 microampere, ID value 100 microampere. So I am writing 100 microampere, and W by L, W by L is given how much, 8 micron by 0.8 micron, means overall value is W by L value is 10. Okay, so these two are given. We have to find the value of VGS. We have to find the value of VGS and VD min. Okay, so what we have to do, first of all we have to write the drain current equation in the saturation region, ID in the saturation region. So it should be written as 1 by 2, okay, K and S, okay, into W by L, VGS minus VT whole square. Okay, this one is 100 microampere. Okay, so I am writing full. It should be 1 by 2. K and S we have already calculated, 194 micro. Okay, write it ampere per volt square. Okay, then W by L. So W by L is simply our 10. So 10, and here I am writing VGS minus VT whole square. So this microampere cancel. Then this should be this 0 cancel. So one can write then this 2 into 10. So 20 by 194 we can write VGS minus VT whole square. Okay, or one can write 20 if we divide by multiple 10 by 97, or if we do the calculation 10 by 97 it is 0.1031. Okay, after simple calculation. Okay, so one can write VGS minus VT is nothing but simply a square root of 0.1031. Okay, so if we do the square root of this term 0.1031, it is nearly come 0.32. So from this expression we can write VGS equals to 0.32 plus VT. Okay, so now VT is given. VT for the NMOS in this question is given 0.7 volt. Okay, so we have to put VT 0.7. So 0.32 plus VT is 0.7. So the overall value will be 0.7, 1.02. 1.02. Okay, so VGS value will be 1.02 in volt. Okay, so this one is also important agent, so we have to highlight 1.02. Okay, so now the device is in the saturation, so we have to find the minimum VDS. Okay, okay, so I am just right, plotting the graph. Okay, so this should be VGS minus VT will be the VDS minimum VDS. After that the device is in the saturation region. Okay, so VD mean or VDS mean we can write, or we can write as VD mean will be VGS minus VT. Okay, so this value VGS value is 1.02 minus 0.7 value. Okay, so it should be 0.32 volt. So the value of VD minimum value for this case will be 0.32 volt. This one is the second part. VGS we have calculated, VDS we have calculated by using simple drain current equation in saturation region, and after simple calculation we have find out the value of this VD min, and it is coming nearly 0.32 volt. So this one is part B. Now we have to go for the part C. Okay, so in part C what we have to do, for the device in B, find the value of VGS required to cause the device to operate as a 1 kilo ohm resistance for a small VDS. For the small VDS, this device for the small VDS in this side, it is in the linear region. Okay, and for a small VDS, it is in the device in the linear region. Okay, so the ID linear expression will be K and S W by L VGS minus VT into VDS minus VDS square by 2. This one is the expression for the linear one. Okay, but here what we have to do, it is already given mentioned that VDS is very small. VDS is very small. Okay, so we have to neglect this thing. Okay, so when VDS is very small, so the drain current in that linear equation can be simply written as K and S W by L VGS minus VT into VDS. Simple, this one. We have to make it 0 because VDS is very small, so square is 0 also, and divided by 2. So we have to make it 0. So this one is the expression when the diode in the triode region, but VDS is very small. So in this case, we can find the value of RDS. Okay, a small signal or source resistance, drain to source resistance. Better to write drain to source resistance. Okay, so drain to source resistance RDS. Okay, that RDS value can be written as RDS equals to this VDS by ID. VDS by ID, because V equals to IR. So R equals to V by I, VDS by ID, like that. You can remember. So VDS by ID. So now from this one, VDS by ID for the small VDS. Okay. For the small VDS. So now this can be simply write 1 by VDS by ID. So simple formula SW by L VGS minus VT. Okay. So this one is the formula for the drain to source resistance. Okay, VDS by ID 1 by K and S, W by L, VGS minus VT. So now it is in the question, it is given. Okay, we have to the causes the device to operate as a 1 kilo ohm resistor, 1 kilo ohm resistor. So we have to find the value of VGS. Okay, we have to find the value of VGS for this one, and this one is given RDS in the question. The value of RDS is given 1000 or 1 kilo ohm resistance. Okay, so now what we can do, once again I am writing the same formula here. K and S W by L VGS minus VT. Okay, so one can write VGS minus VT equals to 1 by K and S W by L RDS. Okay, we have to put it there. So 1 by K and S is already known to us, 194. Okay, W by L. Okay, so in this case W by L is given or no? Okay, W by L. So this one is simply 8 by 0.8. So okay, it is already given. So we have to make it 10. W by L value is 10. Okay, W by L 10. Okay, so make it 10 into RDS 10 to power 3. Okay, so 194 into 10 into 10 to power 3, and this one is in micro. Okay, this K and S is 194 microampere per volt square. So 194 into 10 to the power minus 6. So it should be 194 into 10 to the power minus 10 to the power minus 2. So it should be 100 by 194. Okay, so simple calculation. So VGS minus VT will be 100 by 194. So if we divide or 100 by 194, it will nearly come 5154. Okay, so this VGS value will be 0.5154 plus VT. So 0.5154, and VT for the this question is given threshold voltage for the 0.7. So if we add these two terms, it is nearly come to 1546. So nearly we can say 1.22 volt. So the voltage get to source voltage required for this question when the device is in the linear region with a small VDS, the get to source voltage will be 1.22 volt. So this one we have calculated, and here it is given RDS for all these things. So this is all about this one, this problem. So we have already calculated everything. So we can write also here the COX value is 4.32 into 10 to the power minus 3 farad per meter square. K and S value will be 194 microamp per volt square. Okay, in this case the VGS value is how much we have calculated. We can see what should be the value of VGS, 1.02. So 1.02, 1.02 volt, and the VD mean will be 0.32 volt. Now for this 100 ohm resistance, the VGS value will be 1.22 volt that we have already calculated. So these are the thing that we have already find out. Okay, so this is all about this question. So thank you for watching this video. Okay, thank you.